Good morning, good afternoon, good evening, wherever you may be in this part of the world. Welcome to another session of my presentation series, and this time the topic is understanding the nameplate details of a high voltage current transformer. My good name is John Kweku Amotu, and I've been a professional electrical engineer for the past 31 years, and I'm based in the United States of America. That is, I've been practicing as a professional electrical engineer for the past 31 years in the United States. Okay, so now let's take a look at it here. Okay, so if you watch my YouTube presentation and you like it, don't forget to select the subscribe button in YouTube. And if you like it, select the like button. Then don't forget to share. Very important to share that knowledge. Okay. And below that, it's my YouTube page that I have tons and tons of information and presentations out there, and for young engineers, development engineers, experienced engineers. Sometimes as experienced engineers, you need basically refreshers, right? Okay. And consulting engineers, sometimes you need refreshers. Basically, this can help you with your annual refresher training. Okay, so now let's jump onto this slide, and basically let's talk about what the functions of a high voltage current transformer. What its purpose. Okay, so its purpose is or goal is to be able to step down the high current on the primary side. So on the primary side, you see very high current, let's say 1200 amps, right? 1600 amps, 1800 amps, and 2000 amps for that matter. And if you look at the scale and magnitude of this high current, there's no way this will be ideal to be connected to an ammeter or a protective relay that requires an input current signal, right? Okay, definitely there's no way, So we have to step it down to a much lower current value, and typical values is 1 amp or 5 amps, right? Okay, so once we are able to step it down through a current transformer to a secondary current of 1 amp or 5 amp, this will be ideal for an ammeter, which is an instrument for that purpose that can be used, or revenue grade, revenue grade ammeter, for calculating your revenue right at the entrance of the substation. And also, it provides the current input into the protective relays, right? For differential protection relay, you require an input, right? For overcurrent protection, you require current input. So 1 amp or 5 amps secondary can be an input into this protective relay. Okay, so this is a typical nameplate data details. That is from a Toshiba. The manufacturer is a Toshiba, and basically it has all the parameters, and we'll go through all these parameters in the coming slide. We have basically different industry players. We have General Electric, ABB, we have Siemens, we have Alstom, and Toshiba, and Hyundai. Hyundai are basically based in Korea, and Toshiba is based in Japan. Okay, so these are the industrial players for this current transformer manufacturing. So now let's talk about the substation layout. Okay, so if you go to a substation, right, how would you be able to identify a high voltage current transformer? As an experienced engineer, substation engineer, maintenance engineer, definitely, once I lay my eyes on it, I'll definitely be able to identify it as fast as possible. Okay, so but what of a development engineer, a young engineer that has just started learning power systems? Right? Okay, there should be a way for this guy to be able to figure out what is a high voltage current transformer and a high voltage inductive voltage transformer and a capacity voltage transformer, right? These two are used for basically to step down the voltage to 115 volts or 69 volts for voltmeter, revenue metering, and protected relay purposes. In the typical protected relay, that requires the voltage input is distance relay, step distance relay. Okay, so for a current transformer, high voltage current transformer, right, it is connected in series, right? So in and out, input and output, as you can see over here. Input and output, right? So that's how you are able to identify a high voltage current transformer. So this two are high voltage. One is basically used for revenue metering because it's right at the entrance of the substation, as you can see over here. So they are connected in series. On the other hand, high voltage inductive voltage transformer and capacity voltage transformers are connected in shunt connection. So this is high voltage inductive transformer or capacity voltage transformer. Okay, they are connected. So it comes in, and what you get is just the secondary output. Okay. Over here is a surge arrestor. So that one is also connected in shunt configuration. So this gives you, a better overview, overall big picture of the layout, how a high voltage current transformer is installed and its location in the substation environment, and how you can easily identify it as a young engineer that is so anxious to learn power systems engineer, as a development engineer, because experienced engineers that are basically have experience in substation engineering and substation maintenance, and we can easily identify it once we see that. Okay. All right. Okay, so now let's go to this slide. Okay, so they say that pictures are worth more than 1,000 words, right? Okay, so you can write 1,000 words, fill up the whole page, or write a book. But only a picture will be equivalent to the 1,000 words that you have put together, right? Okay, so this is a picture of a high voltage current transformer, as you can see over here, in, out. So this is the primary conductor. Right? And it's a singleton. Okay, so this one is rated probably to 1,200 amps, 1,600 amps, 1,800 amps, 2,000 amps, 3,000 amps, right? Any of these. Okay. Then basically, its goal is to basically scale it down to 5 amps or 1 amps, right? Coming out of here, right? So the secondary side is on the side. 1 amp or 5 amps that goes to an ammeter or revenue grade metering device or protected relays that utilizes current input, and typically it's differential protection, distance protection. Remember, distance protection utilizes current and voltage signals, and overcurrent protection. So the output, the secondary wiring basically comes out of this box. So over here is basically the different types of cores, right? Okay, so basically it comes in here, and basically the different types of cores, and basically to give you your different secondary voltage, secondary current. It's in here. Okay, so an area view of the substation, right? Okay, so you have basically from this structure comes in and out. Okay, so this one is a high voltage current transformer. Input, out. Okay. On the other hand, on the contrary, for a high voltage inductive voltage transformer, it's connected in shunt configuration. Okay, so you have an input and you only get an output, the secondary side. So that is the difference. And this side is a secondary. Okay, so now let's take a deep dive into what can be found on the nameplate. That is the nameplate details, right? Okay, so the first one is the manufacturer, right? And I think I made mention of a few of the industry big players in the manufacturing of high voltage current transformer. Okay, so let me refresh your memory about that. We have ABB, also called Asaya, Brown, Boveri, Hitachi. ABB basically, changed, Hitachi bought the high voltage equipment component side of ABB, and so they are now known as Hitachi. Siemens, Toshiba, GE, Alstom, and Hyundai. Based in Korea. Okay, so now next one is the type or model. Okay, so you see the type of model, and usually the type of model, they have letters and numbers that is tied to your highest system voltage that it is applied. Okay, so if it is 230 kV, you see that you see 245. Okay, so you see LT 245. Then the insulation level, right? Okay, so the insulation level, we have RMS and peak. Okay, so the RMS voltage insulation level is basically tied to the power frequency over voltage. Okay, so when do we get power frequency over voltage? So that is let me refresh your memory on that. Okay, so if you have phase to earth fault clearing, right? After the fault clearing, you can have an over voltage condition for a short period of time, right? Ferranti effect. And what is Ferranti effect? Ferranti effect is basically if you have a longer cable, and because of the high capacitance effect of the cable due to the insulation system, right? And if the end of the cable is connected to a no load or lightly loaded, right, you will have an over voltage condition at the end of the load. And usually they resolve it with a shunt reactor to be able to regulate the voltage at the end of the line. Next is ferroresonance. Okay, so if you have a L and C element, passive elements in the equipment that basically integrates with external inductors and capacitors, it can basically form a resonant over voltage condition. So these are, just to name a few, these are the various phenomena that can result in power frequency over voltage. Okay, so the phase to 8-4 is something also called a fault recovery as well. Okay. Next is a peak. Okay, so a peak basically comes into play, and basically you see that on the nameplate is shown as a basic insulation level, right? And that is from lightning impulse, from a lightning strike, and switching impulse voltage from operation of circuit breakers. Right, the operation of circuit breakers can also result in above voltage condition. So that is what the insulation level. Okay. Then you also see that the standard that was used to design and manufacture the high voltage will be stipulated on the nameplate. Next is the rated current. Rated primary current. So you see it as 1200, 1600, 1800, 2000 amps, 2500 amps, or 3000 amps, whichever is applicable. So next is an instrument safety factor, and this comes into voltmeters. Right, they have a safety factor basically that comes into play. If you should have 5 times the nominal current, so let's say 1600 amps, right, and you should have 5 times, that's about 8. So it should be, the instrument should be able to withstand that, for that spike in primary current. Okay, so that is what the instrument safety factor is, and basically produce faithfully the required measurement output. Next is the accuracy limit factor. Okay, so accuracy limit factor, usually you'll see it like, let's say 5p or 10p for protection CTs, right? Okay, so it means that 5 times the nominal short circuit, the maximum short circuit current that flows, it should give you an error not more than 5%. It should stay within that error. That is less than 5%. Then 10p means that the maximum short circuit flow 10 times of that should give you not more than 10% error. It should be less than that. So that is what the accuracy limit factor is, and you usually see it for protection CTs, 5p and 10p. Next is the extension current, right? Okay, so you see the extension current based on different ratios and different cores that are used. Next is the knee point voltage, and that is very important, especially for CTs that are used for protection, right? Okay, so this is the linear region, right? And this is the non-linear region. So you have your extension voltage and extension current, right? Okay, so this is the knee voltage, right? Okay, so it will give you the knee voltage that you shouldn't exceed. So that is the voltage that is applied to the secondary side of the CT with other sources open circuited. Next is the rated short circuit current. So you see the rated short circuit current, let's say 40 kA for 1 second or 3 seconds. So that itself tells you that the symmetrical short circuit rating, it's 40 kA in for a period of 1 second or 3 seconds. Next is the peak. So that is the maximum, right? That includes so let's say if a circuit breaker opens, right, and it's trying to reclose into an existing fault, they call it a making current, and that's a peak current, and usually it's 2.5 times this rated short circuit current. So 2.5 times 40, that gives us about 100 kA. So that is our rated peak or making current that the CTs can withstand due to the circuit breaker reclosing into the system. Okay, so now rated system voltage. Okay, so definitely, the CT, high voltage circuit breaker, is connected to a bus, right? Let's say 230 kV, right? So your rated system voltage will be 230 kV, and your maximum, your highest, will be 242 kV, right? So basically, your highest system voltage is basically what ties us into the power frequency over voltage. Yeah, these are our limits. Okay. Next is our rated frequency. Okay, so 50 hertz or 60 hertz. Then the thermal burden. Okay, so let's say emergency conditions, you have to operate this CT, let's say 1.2 or 120 times of 600, right? That is about 1920 amps, right? Okay, so that itself will result in some heating, right? So you should be able to design your connected burden. Your connected burden is your voltmeter and your protected relay. They should be able to withstand this amount of burden due to this increase in current. So that is what the thermal burden is. Then you also see the total weight of the current transformer, right? Total weight of the SF6 gas that is used as an insulation medium. On the other hand, if you have oil that is used as an insulating medium, you'll see the total weight of oil, right? Either oil or SF6 gas. And for that matter, if SF6 gas is the insulating medium, you see the pressure level, the maximum pressure level that you're supposed to fill it at based on ambient temperature charts. Then the thresholds for alarms, right? And the thresholds for tripping, because if the gas pressure gets to a certain point, you don't want to operate the circuit breaker. Actually, the circuit breaker will operate. Then the year of manufacture. Then you also see the maximum resistance, secondary side resistance at 75 degrees Celsius, corrected to 75 degrees Celsius for all the secondary coils, 1 amp and 5 amps taps. Then you also see the required VA bearing that you're supposed to maintain to achieve the required accuracy. Then you also see all the secondary terminals based on the different cores that you have. And for this example, we have a 5-core that we are utilizing to achieve 5 different secondary voltages. So the first one is the manufacturer is Siemens, and like I told you that there are different manufacturers, and I've listed a lot of them of the industry big players in manufacturing. Next is the type or model. Okay, so this one is SAS 245. So 245 tells you that 245 is your highest system voltage. And this CT is adequate for 230 kV nominal voltage rating. So next is the insulation level, right? And I told you that the first one is power frequency, and that is 2 times the nominal rating, 2 times 230. So that's 460 over here. So the next one is BIL. That is for lightning impulse and switching impulse. Okay. Next is the standard. In designing and manufacturing high voltage current transformers, you need standards. So this one is IEC standard that is utilized. Then the nominal current rating, the rated primary current rating. Okay, so if you have the CT over here, right, you have the primary conductor. This is what goes in and comes out, right? So 1,200, 1,600 for this model. It's 1,600 is what comes in and comes out. 1,600 amps, right? So this is your primary current. Then the total weight of the whole CT assembly. Okay. Then the short time current rating. In this one you have 40 kilo amp for 3 seconds, and that is the symmetrical rating. That's how it was done. Dynamic is the maximum, the peak, right? And that is basically based on a circuit breaker reclosing into an existing fault, and that is called making. And the making has to be a peak fault. That is 2.5 times the short time current. So that's about 100 kilohertz. Next is the frequency. So either 50 hertz or 60 hertz. Then the rated continuous amps. Okay, so like I told you that sometimes during emergency conditions, you want to exceed the thresholds, right? Okay, our rated primary is 1600 amps, and sometimes you have an emergency condition where you need to have more than that, so you are allowed at 120% of that continuous. Okay, so that is 120% times 160 is 1600 amps, and that gives us 1920 amps. So that is how the maximum current. And if we want to go more than that, let's say 150%, then that should be for about 30 minutes. Short time, not more than that. Next is the weight of the surface gas that is used for insulating, right? If it is oil that is used for insulating, you see the oil, the weight of the oil, right? Okay, so now this is the primary conductor you see over here. So this is what the tubular bars that you see at the substation, right? Or the drop-down conductor that you see over here, right? That comes in and goes out. On the secondary side, we have 5 cores, right? As you can see over here, 1, 2, 3, 4, 5. That is utilized to achieve 5 different voltage currents. Okay, so as you can see over here, 1S1, 1S2, right? Okay, so let's take a look at the secondary winding over here, right? 1S1, 1S2, right? Then in between that, this is 1S2 and this is 1S3. Okay, so between 1S1 and 1S2, I'm able to achieve 800 amps to 1. Then between 1S1 and 1S3, I'm able to achieve 1600 amps to 1 amp secondary. Okay, so that is basically what this is for, right? It's a multi-tap, right? So in between 1S1 and 1S2, I'm able to achieve 800 amps to 1 amp. Then in between 1S1 and 1S3, I'm able to achieve 1600 amps to 1 amp. Okay. So the same applies to 2S1. That's the second core. 1S is basically the first core. Then 2S1, 2S2, 2S3 is the second core. So similarly, for the secondary terminal, same thing. Between 2S1 and 2S2, I'm able to achieve 800 to 1 ratio. Then between 2S1 and 2S3, I'm able to achieve 1600 amps to 1 amp. Similarly, for the third core, that is 3S1, 3S2, 3S3, right? In between 3S1 and 3S2, I'm able to achieve a step down current of 800 amps to 1. Then from 2S1 to 2S3, I'm able to achieve the following, that's 1600 amps to 1. Over here. Okay, so now let's go to the fourth one. The fourth one is just between two windings, that is 4S1 and 4S2. Okay, so for that one, between 4S1 and 4S2, I'm able to achieve 800 is to 1. Then in between that, I'm also able to achieve 1600 amps to 2 amps. Next is the fifth core. So this is the fifth core, this is the fourth core, this is the third core, this is the second core, and this is the first core, right? So between 5S1 and 5S2, I'm able to achieve 800 to 1, and 5S1 to 5S2, I'm able to achieve 1600 to 1. Okay. So for the ratio, we have 1600 is to 1 and 800 is to 1. Remember, I'm able to achieve 2 ratios, right? 600 800 over 1, 800 over 1 for the first core. So this is the first core, second core, third core, fourth core, and fifth core, right? And these are the ratios that are achieved. And for the second core, I'm able to achieve a 1600 to 1 and 800 to 1 ratio. The third core, I'm able to achieve a 1600 to 1 and 800 to 1. In the fourth core, I'm able to achieve a 1600 to 2, 1600 to 1, or 800 to 2, 800 to 1. And for the fifth core, I'm able to achieve a 1600 to 2 and 800 to 1. Cool. Now let's talk about the VA burden. Okay, so the VA basically burden is the connected burden. Basically, what is telling me that I shouldn't exceed the burden that I'm going to connect. Right, that is the voltmeter and the relay, protected relay. I shouldn't exceed more than 20 VA. Both for both ratios that we are utilizing, 800 is to 1 and 1600 is to 1. Next is the accuracy class, right? In basically PX is for protection, right? As you can see over here, for protection, right? And this one is for mirroring. So protection and mirroring is telling me that my accuracy class is 0.2. That is 0.2 error. And that is the best error for a voltmeter, and that is the finest error. I shouldn't exceed that and be able to reproduce faithfully the current signal. Next is the instrument safety factor and accuracy limit factor, right? And that is very important for instrument and for ammeters, right? So ammeters, 5 times the nominal current. So 5 times 1600, I should be able to withstand and reproduce faithfully the secondary current of 1 amp or 2 amps. That is required. Next is that the knee point voltage, right? So these are all the knee point voltages that can be achieved on the secondary side to achieve the highest accuracy, because a step change of 10% increase in excitation voltage or secondary side voltage results in 50% increase in excitation current, and that is the non-linear region and saturation region, and we don't want to get there, right? So that is why basically the knee point voltage is right here. Okay, we draw this. Okay, so this is the knee point voltage. So this is the linear region, and this is the non-linear region. Next is the excitation current, right? Okay, so that is the magnetization branch, right? You have a resistance, and then you have a so you have a excitation current that basically goes here, right? Okay, so it's telling me the maximum excitation current in milliamps that I can achieve for the different CT ratios and the different core configurations. Next is the maximum resistance for each core and secondary output. Okay, so between 1S1 and 1S2, I have 8 ohms corrected at 75 degrees, and between 1S1 and 1S3, I have 4 ohms. Right, so it tells me all the resistance values that I'm achieved for the different secondary cores and the different ratios that is required to be achieved. Now let's go to the gas filling, right? Okay, so definitely you have a gas that is being used as an insulating medium for this high voltage current transformer, right? Okay, so you have to know the pressure level, the maximum pressure level. So for filling, it's telling me that 6 bars is the maximum that can be achieved at the temperature of 20. Okay, so if you don't have that temperature, basically you need to use the correction charts, from the instruction manual that will tell you the corrected, filling pressure that you're supposed to, and also it gives you the alarm if you should have the SF6 gas pressure dropping, the alarm that you're supposed to have, and also for tripping, that is to prevent operation of the CTs. Okay, so now we are on the last slide. Okay, so after watching this video, my presentation, if you like this presentation, don't forget, go to YouTube and select the subscribe button. Select this, select the like button, and the like button, then share. Don't forget to share. And also go to this my YouTube channel. There's tons of presentations, technical presentations that can help you. As a young engineer, you are about to start your career in power systems. Right? This will help you, to gradually develop your career. As a developing engineer, mid-career, definitely you need a refresher. So you can go there, and there are tons of presentations out there, technical presentations out there that can basically help you to refresh yourself. As an experienced engineer, we all need refreshers on a yearly basis. Go there. There are tons of videos and presentations out there that will help you to refresh yourself with the knowledge and expand your knowledge. And as much as you are an experienced engineer, there are certain things that are areas that you might even not know, and this will help you to add more knowledge to what you already have. So don't forget to look out for much more presentations coming out and very interesting topics. With that, I say thank you so much.